This document is the schematic for the Arduino Uno board. So this has been on Canvas all semester, but you haven't really needed to reference it directly. And I'm pulling it up because of something neat that I want to talk about that kind of is going to hopefully force you to see if you remember op amps and resistors and all that stuff from earlier in the semester. So the poll everywhere question I'm going to launch in a second is an open-ended question. I want you to tell me what this part of this circuit does. Okay, with a couple tips or hints I'm going to give you on the way. So they are using boxes to represent resistors instead of a little squiggly line, right? So that equals a resistor. This thing right here, that is a P-channel MOSFET, so the opposite of an N-channel MOSFET that we learned about. Basically, the behavior is reversed. It goes off when the gate is high and turns on when the gate is low. It's also rotated 90 degrees, so the gate is the pin up there at the top, not on the left. Okay? Other than that, you've got op amps you've seen before. Anywhere that it says this plus 5 volts here, you'll see that in multiple places in the circuit. Those are all connected. Okay? Just like we have multiple ground symbols, we talked about this earlier in the semester, rather than drawing lines all over the place to connect all the grounds, we just use, so they're using GND instead of the little 3 parallel lines. Okay, so anywhere you see a GND or a 5 volts, those are connected. USB VCC here, that stands for the 5 volts from your USB port, right? When you plug the USB in to power the Arduino. And then over here, this thing is the barrel plug. So you can also power the Arduino from your 9 volts or from a wall adapter, right? And you see the little label here, power in, that's the center pole of the barrel plug, okay? So the outer sheath of that is ground, so you see that's connected to ground here. You see power in, goes through a diode, and then that is connected to VIN. This VIN, which is accessible on a pin on your Arduino, is labeled VIN, is the same VIN that's over there. Okay, given all those little bits of information, and activate the poll, what does the highlighted or boxed part of this circuit do? Okay, no code running on that part, it's just hardware. What's it doing? See if you can figure it out based on what you hopefully remember. We got resistors, op amps, a transistor. The part I boxed there doesn't have any capacitors in it, but there are some capacitors over there I'll talk about a little later. So almost everything we covered earlier this semester in one useful little circuit. What does it do?
There's a pole that's up now. Up at your pole. How do you say open? Oh, watch my coffee.
I think it. We think that's sort of. No, it's like that. The part that's in the hierarchy. You sit here. No way, it's in there. Terrible habits, which is not correct.
We're only at about 45 responses, so give this a few more minutes. Talk to the people around you if you have no idea what's going on.
I have two more. Yeah, I think the
This is fine. I am not.
They always run out to what's in retail.
And maybe as another hint to thinking about this, there's two different ways you can power your Arduino, right? You can plug it into USB. You can plug something into the barrel jack. You can also plug in both at once, right? The USB and the barrel jack. So think about the different possible combinations there and how the circuit would behave differently depending on what's plugged in. You can tell if somebody just killed a mosquito or is like really excited that they figured the circuit out. I'll give this like another, until the wall clock hits the 5 it'll load again. I think that's a little slow, but give it like another minute, minute and a half. All right, another minute.
That's true. So I'm working on
All right, 30 seconds.
manufacturing is coming back to the US. Everyone wants someone with experience. That unfortunately is what most experience.
15,
First job was
10,
my second job was
5, 4, 3, 2, 1, deactivate. All right, let me check some of the replies. All right, hold on. Response history, there we go. Decrease input, regulate current from both sources. I don't know, I just got here. Current to voltage converter comparison QN. Okay, I see. Okay, I see a few people who got the right idea here. So does anybody who is pretty confident you got it care to explain or venture a guess? If not, I'm going to pick on you because I can see your name so I know who got it. Somebody might as well volunteer. What does it do? Maria, I'm going to pick on you because you're the first one I saw who got it right.
So it compares. So it's a comparator. I don't know why we're using the voltage divider, but we divide to UIN. The voltage UIN. Oh, it's
VN, yeah.
Yeah. To 3 volts. And then if it's sufficient, then it's passes it. And if it's not, oh no, if it's sufficient, it passes it USB.
Close enough. Right idea. Okay. So, and I'll kind of repeat that because I know in the back you might not have been able to hear. So remember, our goal at the end of the day, the Arduino operates at 5 volts, right? We need 5 volts for the digital logic pins, and it also just has the 5 volt pin. So, if you just plug in the USB cable, USB is already a regulated 5 volts from your computer or wall adapter or whatever it is. This MOSFET being P channel is on by default, so it just passes the USB 5 volts to the rest of the Arduino. Great, easy. So that's what this little up to 5 volt thing is there. If you don't plug in the USB and you plug in the barrel jack instead, the Uno accepts something in a 7 to 12 volt range. So you can power it with a 9 volt battery, right? Okay, well how does 9 volts get converted to 5 volts? That is this little box here, which is representing a voltage regulator, something we did not talk about too much this semester. I mean, way back earlier when we looked at RC circuits and cell phone chargers and stuff, we talked about this sort of thing a little bit. There's linear regulators, which are basically just a voltage divider kind of burning off that extra voltage in a resistor. There's something called a switching regulator, which is charging a capacitor and does it more efficiently. We didn't go there. The point being, this has an in and an out. In accepts a voltage in some range, out outputs a more stable 5 volts. There are some capacitors there to act as filters. Remember, capacitors act as kind of a short circuit for high frequencies. So if there is any noise on that, it kind of short circuits the high frequencies to ground and ideally gives you a stable, again, 5 volts connected to the rest of the Arduino. Cool, if you plug in one of those things at a time, you're good. But what happens if you plug in both? How does it know which one to draw power from, or does it try to draw power from both at the same time and kind of risk shorting them together? That's where the op-amp comparator comes in. Okay, so Maria, you asked, you weren't sure why there was the 3.3 volts there. Remember, it requires a minimum voltage of about 7 volts. So we send V in, which is coming from the barrel jack. That gets divided in half. Okay, here's just a voltage divider with 2 10 kilo ohm resistors. Okay, and then that goes into a comparator where it's compared to 3.3. So technically 7 divided by 2 is 3.5, right? But so it would accept 6.8, 6.9 or whatever. But if that Vin is 0, or if that voltage is too low, right? If I try just powering it on the barrel jack with a 3 volt battery or something, that voltage is too low, the output of the comparator is low, the MOSFET stays on and it powers from USB. If that voltage gets high enough, okay, if Vn gets above 7 volts, then the output of the comparator is going to flip high and shut this MOSFET off and cut off the USB power. Okay, so basically, once you plug in either a wall adapter or the 9 volt battery, it cuts off the USB and says, okay, we're not going to draw power from the USB anymore. So that's how it knows which one to use. And so if you remember, at some point earlier this semester, I forget if it was in an announcement or on Ed or whatever, but Dave Hartino said, like, hey, you should always be powering your Arduino off the wall adapter because it's going to cut off this USB power, and then that can help, if you do mess up wiring your H-bridge or something, help prevent kind of that issue with, oh, my code won't upload because it's making the USB upset. Like if you have this shorted to ground somewhere, right, and this MOSFET is on, then you're shorting your USB power to ground, and that's going to make your computer's USB port unhappy or potentially damage it. Okay, so again, you don't need to do anything with this. It's already designed for you. It has just been there kind of happily chugging along all semester, but hopefully as a result of having taken this class, you can look at that diagram and be like, oh, I actually kind of understand what that's doing. Even if you didn't figure it out on your own, hopefully based on what we did earlier in the semester, that'll make sense. Okay, so that's kind of, again, the lead-in for today. What we're going to be doing for the rest of today, since there is no final exam, is going back through the concept test that we did way back on day 3 of lecture. Hopefully to jog your memories, and hopefully for my sake to show that I taught you guys something and we don't just have the same results we did on day 3 when we do the concept test at the end of the semester. But rather than just leading with a pure resistor problem, I kind of wanted to do something like this that combined a whole bunch of stuff. So with that, what we are going to do for Pull Everywhere, rather than making 30 different questions, I'm just going to make one and leave it open. So you're just going to change your answer for each question, and then I'll close it at the very end, and you'll get the credit just for that one question. But I didn't feel like starting and stopping 30 million different questions. So I'm going to activate the next one in a second, and we are going to go through this whole concept test as fast as we can on the, I'm going to zoom back out. I think it was a 3rd day of class. I stopped to explain a lot of these, and there were clearly some initial misconceptions we needed to clear up. Hopefully this time we get a lot more right, but there might be some where maybe I'll kind of, depending on how much time is left, we'll do a little explanation, because again, these are things I want you to come out of this class knowing and not still getting mixed up, okay? So I'm going to activate And again, we're going to try to go rapid fire here because there's like 30 of these, so we have like 1 minute per question. In this circuit, resistors B and C are in series, parallel, both, neither, or I don't know. Okay, be quick, 10 seconds. 5, 4, 3, 2, 1. Responses. Parallel, B. 85% of you got the correct answer, which is yay, an improvement from 66% at the beginning of the semester. Okay. I can't tell if you guys are applauding for yourselves or for me, but I'm glad that I taught you what series and parallel resistors are. That was for me. Okay, and again, don't worry about changing it until we go to the next question. Okay. All right. Now I'm kind of going to hide. Which branch or section of a circuit has the least resistance between its endpoints? Branch 1, branch 2, they are the same, or I don't know. Okay, let's do quick. 10, 5, 4.
Wait, it's
No?
not, it's still the old one.
Oh, wait, well, yeah, you're just, I'm not launching a new one, you're just changing your answer. Does it let you change? Okay, everybody good? Again, I'm not closing and reopening a new question each time. We're just going to keep using the same question. Okay? Okay, now that we got that, let's check responses. Okay, 99% of you got branch B, branch 2, B, yay. Okay, up from 77%. Lovely. Okay, so for the 1 or 2 people who didn't get that, remember your resistors in series and parallel. Okay. How does the power dissipated by resistor A change when resistor B is added, as shown in circuits 1 and 2 respectively? So you got resistor A, value R, connected to some fixed battery, voltage V. We add another resistor in series with it. Does the power dissipated by resistor A increase, decrease, or stay the same? Getting slightly more difficult here. Okay. 10, 5, 4, 3, 2, 1. Correct answer is B, decreases 82%. Okay, so that is a significant, okay? Not 100% though, so add another resistor in series, this total resistance increases. Ohm's law, current through the circuit is then going to drop. Power dissipated by an individual resistor is P equals I squared R, right? So if the current through that resistor goes down, the power dissipated by that resistor went down. Okay, I think maybe there's a temptation to look at that and go, oh, it's gonna stay the same because, I don't know, you didn't change something about this resistor, but adding that second resistor decreases the current, power goes down. Okay, much better than the beginning of the semester. All right. Staying on the power topic here, in which circuit or circuits does the resistor dissipate the least power? Okay, so I realize Poll Everywhere doesn't let you, I think the last time we tried this, it doesn't actually let you select more than one answer, but it lists D, and F, so you shouldn't need to, okay? So if it's some combination.
We can't select, I don't know, I guess.
Oh yeah, did I not put in a G? Okay, if you don't know, then just don't answer it for now, and then you'll put in an answer for the next one. Okay? In which circuit or circuits does the resistor dissipate the least power? 10.
Isn't the voltage the same?
You can assume the voltage V is the same for all of those batteries. Okay?
Isn't it circuits 1 and 2?
10, 5, 4, 3, 2, 1. Correct answer is circuits 1 and 2. Which D. Okay, most of you, don't change your answer real quick because I want to jot the percentage down. We got 68%, which is again more than the. Okay, you guys are really going to clap for every single one of these. Okay, unless we get to a point where you do worse somehow. Hopefully we don't. Okay, so yeah, the trick here, again, the kind of beginning of semester trick was that if you add more batteries in parallel, that does not actually increase the voltage drop over that resistor, so the power dissipated by the resistor stays the same. Clearly, in the third circuit there, 2 batteries in series does increase the voltage, so in the ideal sense, there's no difference between circuits 1 and 2 there. The voltage across the resistor is the same. Okay. How does the resistance between the endpoints of the branch change when the switch is closed? Increases, decreases, or stays the same? Switch is initially open. And measuring the resistance between the 2 endpoints, how does that resistance change? This one should be pretty quick. Let's do 10.
Less?
5, 4, 3, 2, 1. 81% of you said B. Okay, which is an improvement, but still means 20% of you don't remember resistors in series and parallel. So again, coming out of this class, that's kind of one of the. Okay, I'm sorry, I forgot to pause for applause on that one. Okay, you close that in the initial. If that switch is open, this resistor is not affecting the endpoint resistance. Close the switch, then these 2 resistors are in parallel. When you add resistors in parallel, resistance goes down. So even though this one is in series there, if the equivalent resistance of this part goes down, then the equivalent resistance of the whole thing goes down. Okay. Which of these 3 circuits are equivalent? We're talking about drawing circuit diagrams here. Okay, no questions about actual voltage or current or resistance or anything. It's just which circuits are electrically equivalent. Okay, let's do 15. 10. 5, 4, 3, 2, 1. 73% of you said D, which is the correct answer. Okay, yes. Large increase from early in the semester, but not 100%. Again, so all of these are electrically equivalent if you trace which nodes are connected where. So the negative node of the battery is connected to one end of each resistor, and the positive end is connected to the other end of each resistor. Even if you just kind of do these wonky rotations or translating them around, doesn't matter how you draw the lines. These lines are just representing ideal 0 resistance wires. So I could draw it like this, right? And it doesn't matter where those resistors are physically on the page. Okay? Next up. I'm going to skip that one because it's basically a mirror of one of the earlier questions about resistor power. Okay. The current through point 2 in the circuit is less than 0.1, the same as 0.1, greater than 0.1, or I don't know. Less than 0.1, the same as 0.1, greater than 0.1, or I don't know. 10, 5, 4, 3, 2, 1. 86% of you said B, the same, so that is still an improvement. Okay. For the 10 or 15% of you who got that wrong. Remember, current does not get used up or dissipate, right? If 2 points are in series, then the current through them is going to be the same. Don't conceptually get it mixed up with voltage relative to ground, right? So if this is battery voltage V, and we define that as ground, that's 0, then the voltage there is V, and the voltage there is 0. So you can think of voltage drop, but current doesn't drop or dissipate or get used up or anything in series like that, okay? What happens to the voltage difference between points 1 and 2 if resistor B is removed? So I take this resistor out of the circuit. What happens to the voltage difference between points 1 and 2? Increases, decreases, or stays the same? And let's do this quickly. 10, 5, 4, 3, 2, 1. 63% of you said stay the same, which is the correct answer. Better than the beginning of the semester. Sorry, 67%. Oh, can you 70? Well, okay. So don't cheat and change the answer after I announce it, because I want to gauge. What can you guys see the percentages right now when I have it?
Yeah.
Okay. But if I click just to put it on the instructions, then do they go away and you can't see the percentages?
We can't see any changes.
Oh, it's still, you still see the graph?
I think it just freezes the graph, so it's like we can't see any changes.
Okay. I probably should have figured that out much earlier in the semester, but oh well. Okay. Better than initially, but maybe still concerningly a little low on that one. Okay, so if I remove this resistor, yank it out of the circuit, battery's still connected, voltage between those 2 points didn't change, right? They're just in parallel. Voltage is the same regardless of how many resistors I add or remove in parallel to a single battery like that, okay? So it does not, even though you, again, might think, oh, I remove this resistor, so this one's gonna get more something, more, they were sharing the voltage, power, current, or whatever. In parallel, voltage is the same, okay? Don't conflate voltage, power, and current, okay? Here is something that definitely tripped people up at the beginning of the semester. The voltage difference between points 1 and 2 is greater in circuit A, greater in circuit B, the same in both circuits. Voltage difference between points 1 and 2. So again, the difference between these two circuits is I moved the ground symbol from the negative terminal of this battery down here to in between the negative and positive terminals of those two batteries. Okay, let's do 10. Five, 4, 3, 2, 1. If my mouse decides to work. 72% of you said C, which is correct, so that is a very big improvement from the beginning of the semester, when most... Okay. The applause is waning in its enthusiasm. I told you guys that was going to be a lot for like 30 questions. Ground symbol, so you see there were a lot of I don't knows coming into the class, right? So hopefully this is something that you learned in mechatronics compared to physics. This is just defining what we call zero, right? Remember we had the whole elevation analogy with the mountain and everything, right? So if we draw the mountain next to this, and I just measure the difference between the bottom and top of the mountain, it doesn't matter what I call zero elevation, right? I can define elevation at sea level or Ithaca or wherever, but the distance between the top and bottom of the mountain doesn't change. Same idea with voltage here. I'm just moving what I define as my 0 points. Okay. Here's another one. What is the voltage difference between points 1 and 2 in this circuit with an open switch? So I got a 12-volt battery, resistor, point 1 is there, open switch, another resistor, point 2 is there. What is the voltage difference between points 1 and 2?
6. But V equals I times R. And if there ain't no I,
Yeah, it's
there
open,
ain't
so
no
there's no current.
Okay.
Because
This one inspired some vigorous debate when we did it earlier in the semester. We'll see.
I'm at least 65% sure.
Let's give it 15 seconds, a little more time to think about this one.
No.
10.
There is no current.
There's no current, so there's no current.
There is no current, so there's no voltage.
5,
Yeah, so
4,
Get
3, 2, 1. Okay, 72% of you said C,
Oh,
which is correct. Heard some heated debate about this up front, so I think we were much more divided earlier in the semester. Again, remember, don't get voltage mixed up with the idea of voltage drop across something, right? So I heard someone up here up front say it. There's no current through that resistor, which means there's no voltage drop over that resistor. Okay, V equals IR applies to that resistor. So if the voltage here is 12, and there's no drop over that resistor, then the voltage there is also 12. Okay, it doesn't mean the voltage there is 0, because V equals IR applies to the voltage drop across the resistor, not just kind of voltage is 0 everywhere. Okay? All right, we'll just skip that one because we did well enough at the beginning of the semester. Okay, switching gears to capacitors. The capacitors all have equal values. Whoops. The equivalent capacitance of circuit 2 is higher than circuit 1, lower than circuit 1, the same as circuit 1.
Oh, it's 1 over. Yep, I remember now. It's been a hot second since we looked at a capacitor, alright? Let me finish my
You don't have
coffee.
the capacity to work it.
I don't got the capacity for none.
Okay, 10,
I think permanently I'm gonna stay for like
5,
that's been chosen
4,
in all my life.
3, 2, 1. 70% of you said B, which is correct. Okay, so capacitors are kind of the opposite of resistors. Capacitance goes down when you add more in series, goes up when you add more in parallel. Again, think about that. If you add capacitors in parallel, it's kind of like adding more surface area, just effectively making a bigger plate, so you're increasing capacitance. If you add them in series like this, you're kind of adding more distance or gap between the ultimate end plates, so that actually decreases the capacitance. Okay, so just because there's more of them doesn't mean capacitance goes up. Okay? Skip that one. All right, getting into how to use a voltmeter. Which diagram or diagrams show how to properly connect a voltmeter to measure the voltage across resistor R2? You can select more than one answer. Although, except not in Canvas you can, that's not true in Poll Everywhere, but if there's more than one correct answer, then just select one of them. Which diagrams show how to properly connect? I feel like it's blurry or not focused now. There we go. A voltmeter to measure the resistance across, to measure the voltage across resistor R2. Let's do 10. 5, 4, 3, 2, 1. 81% of you said B, which is correct. Okay, so a lot of people did come into the class knowing how to do that, but glad we have seen some improvement. If you got that wrong, remember, multimeter goes in parallel to whatever you want to measure the voltage across, right? So all of the, pretty much, this one's measuring voltage across R1. Those other two are in series, so they would be measuring current, right? If you want to measure voltage, you've got to connect the probes in parallel like that. Okay. I'm going to skip that one. Kind of just talked about current, so I'm going to skip that one. Okay, we've done a ton with the breadboard, so I'm going, let's do the breadboard one, why not? So, depending on how well we can see this. Okay, which LEDs, actually this is going to be, it doesn't let you do multiple selects, so we're going to skip that, but again, remembering how holes in a breadboard work, for example, LED B here would not light up because the leads are in an adjacent row, so there's an open circuit between these two rows and no current through the LED, whereas LED A is in the same row as the resistor and jumper wire, so A would light up. And then similar, I think, C and D, one of them's right, one of them's wrong, but not going to do that as a pole. All right, more capacitor stuff. In this circuit, the voltage Vs has been a constant positive value for a long time. The current through the circuit is Vs over R, 0, infinity, or RC. Okay. 10, 5, 4, 3, 2, 1. 75% of you answered 0, which is correct. That is a big improvement. Okay, if you did not get that right, remember capacitors act like an open circuit in steady state, so the key word or key phrase there is for a long time, which is also engineering speak for saying it's in steady state, right? So if the capacitor is acting like an open circuit, then you can't have any current, okay? Now, for the circuit in the previous question, which again I guess I will redraw here real quick. So we had a battery like that, a resistor and a capacitor. The voltage Vs suddenly changes to 0. So this voltage goes from some positive value Vs to 0, and then V out is there. Which of the following graphs represents the behavior of V out after Vs changes? So Vs was positive, it goes down to 0. What does a graph of V out versus time look like? A, B, C, or D? Okay, 10, 5, 4, 3, 2, 1. Oh, we're split. Interesting. We have about 35% of you saying B and 36% of you saying C.
Oh, we took the L.
So,
No.
it's, I don't know where, so everybody who said B, you had the voltage like starting at double Vs and then going to Vs. I don't know why, but C is correct here. So it would have started at Vs and then gone down to 0. So remember when you did this in lab or on the homework, right? If you drove the circuit with a square wave, then the RC output kind of charged up, discharged, charged up. So this question is asking about this part of that graph, right? Where the output changed from some positive to 0. So, okay, clearly I need to do a better job teaching RC circuits and time constants next time. Because, oh wow, I actually got worse. Okay, I didn't notice that at first. Okay, put a little asterisk on that one, and I will need to look into that more next time. All right. Okay. I did not do a good enough job hiding the answers here. For the circuit in the previous question, so again, resistor, capacitor, I'm not going to redraw it. The constant voltage source is replaced with a sinusoidal voltage source with an amplitude Vs and frequency F. As F gets very large, what happens to the amplitude of the output voltage? Okay, is it equal to Vs over R? Does it approach the input voltage amplitude? Does it approach 0? Is it equal to Vs over 2? Again, same circuit we had previously. Again, resistor, capacitor, V in, V out. V in is a sine wave. So we're asking what happens to the amplitude of V out as the frequency of that sine wave gets very large. 10, 5, 4, 3, 2, 1. Okay, 47% of you said approaches 0, which is correct, but a lot of people said B. We were at like 30-something% for B, so you're getting your high and low pass filters mixed up. Remember, low pass, resistor comes first, then the capacitor. High pass, the capacitor comes first. So for a low pass, as the frequency gets really big, the amplitude of the output is going to go to 0. Okay, so at least we were up from our, we had a lot of I don't knows initially because people didn't see this in physics, so better, but still some confusion between high pass and low pass. All right, so let's see. There's about 6 minutes left, so let's see how much of this we can get through. All right. Op amp time. Compared to circuit 1, what happens to the output voltage Vout when a load resistor, RL, is added to the op amp circuit as shown in circuit 2? Assume the op amp is ideal. Okay. Does the output voltage get bigger, get smaller, or stay the same? Okay, let's do this one quickly. 10, 5, 4, 3, 2, 1. 68% of you correctly said C, it stays the same, which is a very large increase since most of you had not seen op amps coming into the class. So remember, ideal op amp assumption, in this case, we just have a buffer or voltage follower. Because of the negative feedback, the output voltage is going to be equal to the input voltage. Even when you attach a load resistor, that does not change the output voltage. Okay. What happened, another ideal op amp question. What happens to the current I plus, so the current there going into the positive input, when the value of RS is increased? Does that current increase, decrease, or stay the same? This quickly, since we're running low on time. 5, 4, 3, 2, 1. And again, 55% of you said stays the same, which is correct. But we had a bunch of people answer B, expecting that current to decrease. So remember that the other one of our ideal op amp assumptions is that the inputs just draw no current. So the value of that resistor doesn't actually matter. If you were thinking Ohm's law, oh, resistance goes up, current must go down, because my voltage didn't change, you would be correct for a normal circuit with just a resistor and a battery, but we're going to the input of the op amp here. The input of that op amp does not draw any current. Okay. Diodes. For this circuit, the source voltage, Vs, is 3 volts. The diode has a forward voltage drop, V gamma, of 1 volt. The output voltage, V out, is 3 volts, 2 volts, 1 volt, or 0 volts. And I'm starting to speed up here since we only got 4 minutes left. 10, 5, 4, 3, 2, 1. 47% of you said C, which is correct. But 32%-ish said B, so you were kind of incorrectly subtracting the 1 volt over the diode from the 3 volts to get 2 volts. But remember, forward voltage drop of the diode just means that drop over the diode is 1 volt. So remember that IV curve for a diode where the ideal graph just kind of looks like this, right, where there's no current for a while until you reach the threshold voltage, and then we treat it like a constant voltage drop, even though the actual graph is more of kind of an exponential thing like that. So since V out is just measured directly over the diode here, that means the output voltage is going to be 1 volt. Okay, we're going to skip a diode question, go up to a BJT question. This circuit shows an NPN bipolar junction transistor, or BJT. Assume the transistor is operating in the active region. The current I2 is always 0, is constant and independent of I1, which is the current into the base over here, or is proportional to I1. We are in the active region. Let's do 10, 3, 2, 1. Okay, 71% of you said C, which is correct. Again, that is a big increase from coming into the class where 81% said I don't know because you hadn't seen transistors before in most cases. So you're going to think of the BJT kind of like a control valve, where when you're in that active region, if you increase the base current, then you also increase the collector current through your load. Okay. MOSFET. This circuit shows an N-channel MOSFET. If the input voltage, VC, changes from 5 volts to 3 volts, does the current I1 increase, decrease, or stay the same? Let's do 10. 5, 4, 3, 2, 1. 58% of you said C, which is correct. And a big increase from a lot of people saying I don't know, and you hadn't seen these at the beginning of the semester. Unlike a BJT, which does draw current through the base, the gate of a MOSFET does not draw any current. So kind of like with the op amp, that current is just always going to be 0, independent of that resistor value. Okay? We have probably like 30 seconds left, and the rest of this is very Arduino based, which is stuff you were all kind of elbow deep in with the robot right now. So timers and registers and things, so I'm not going to bother doing those. But overall, I think we saw an improvement, so well done. Again, if you still don't remember resistors in series and parallel though, double check, because you don't want to come out of this class not knowing kind of the basics that you should have known from physics, okay? All right, thank you. Go build robots. I'll be around for questions as usual.